So let's try another example of an alternating series. This one's written very different, right? I don't even have a general formula for the nth term of this series. And in fact, it would be pretty difficult to write that. Looks like my numerator switches back and forth between 2 and 1. That's already difficult to write. And my denominator goes up by 1 every other term. So it would be very difficult to describe this. Let's see if we can use the alternating series test here. So my first question would be, does the nth term approach 0? In other words, if I go really far along in this series, will I eventually be adding terms that look basically like 0? Okay, so my denominator is getting bigger and bigger, and my numerator is either a 2 or a 1. So yeah, I'm kind of convinced I would generally have either 2 over a huge number or 1 over a huge number. And either way, that does approach 0. So for my first criterion, yeah, it is true that the limit as n approaches infinity of an is equal to 0. Alright, my second criterion, I want to see if my terms are always decreasing. Well, let's look. So early on, I've got 1/2 and 2/3. That's not decreasing, that went up. I've got 1/3 and 2/4. Ooh, that went up too. So it turns out this guy's going to be increasing like all over the place. So I'm definitely not guaranteed that it's going to be decreasing the whole time. So this is the first time we've seen an example where we have an alternating series, but I can't really use the alternating series test. Now here's the temptation. The temptation is to say, well, because number 2 isn't true, let's just go ahead and say it diverges. But that's not really how this works. The alternating series test is only used to determine that a series converges. It's never really going to be useful to tell us that a series diverges. So this thing still might converge or it might diverge, but I'm going to have to turn to a different tool to determine what happens here. So what I want to suggest is that we actually just go ahead and group these guys together. So let me clean up my annotations for a second. I'm just going to look at each pair of terms, and we'll see what happens with that. Okay, so if I look at each pair of terms, the first one is 2 over 1 minus 1 over 1, so that's 1 over 1. My second pair of terms, 2 over 2 minus 1 over 2, that's 1 over 2. My third pair of terms, 2/3 minus 1/3, 1/3. Okay, and what you can see is that every time I combine a pair of those terms, I just end up with the next term in the harmonic series. Well, we've actually already studied the harmonic series. You can either just know off the top of your head it diverges, or you could call this a p-series with p equals 1. And once again, we know it diverges. So because I was able to rearrange this guy and rewrite it as equal to the harmonic series, I know that this diverges. I would say the series diverges. And really, I just need to mention somewhere that this is either the harmonic series, or I could say it's a p-series with p equals 1. Either of those would be a sufficient explanation here. But the big takeaway from this problem is, just because the alternating series test doesn't work, doesn't necessarily mean that your series diverges. Sometimes we can't use this test, but it still might converge or diverge. We always have to use some conclusive tool to get to our answer, though.